Imagine taking a highly technical coding problem, specifically optimizing a GPU kernel.
Right, which is already incredibly complex.
Exactly. And you run the baseline code, and it takes about 419,000 microseconds to process a batch of data. Your goal is to just make it faster.
Which usually means squeezing out like maybe a 10% gain if you're lucky.
Yeah, but now imagine speeding up that exact same task by 232 times, dropping the processing time all the way down from 419,000 to just 8,805 microseconds.
It's just a staggering leap. It's almost unheard of.
It really is. But the real hook here isn't just that massive speed up. It's how the optimization was actually achieved, because you aren't writing every single line of code yourself.
Right, you're acting more like a manager.
Exactly. A manager directing this whole swarm of AI agents to do the heavy lifting for you. They test the hypotheses, they write the algorithms.
And in the world of low-level GPU optimization, getting a 232x multiplier means you're completely redefining the structural approach to the problem.
And we are doing a deep dive today into exactly how that structural redefinition happened. We're looking at a super detailed blog post from July 2026 by a developer named Sandkalp.
Yeah, he entered this auto research contest hosted by GPU Mode and Core Automation.
Right, and he placed 12th out of 183 participants.
Which, I mean, that is a formidable achievement when you look at the leaderboard. He was up against people who build these systems for a living, principal engineers at major hardware companies.
Totally. So the mission for our deep dive today is to explore Sandkalp's methodology. How he used tools like Codex, which runs on that GPT 5.5 architecture, along with Claude Pro, to basically build an automated research lab.
It really was a lab, a fully autonomous setup.
Yeah, we are going to unpack the massive mathematical bottleneck his AI had to solve, the clever ways he steered his agents through, like 1,500 autonomous code submissions over just 14 days.
That volume of testing is just insane to think about.
Right. And we'll get into what this experiment reveals about the future of problem solving. Okay, let's unpack this. Starting with the core technical challenge. Because even if you aren't, writing low-level code every day, the underlying constraints here are actually surprisingly intuitive.
They really are. So the contest challenged participants to implement this very specific mathematical operation. It's called batched square compact householder QR factorization.
Which is a mouthful.
Yeah, it's usually just abbreviated to QR decomposition. And they had to do this for matrices, so grids of numbers, ranging from small 32 by 32 grids all the way up to these massive 4096 by 4096 grids.
Using FT32 CUDA matrices, right?
Exactly.
Let's define those terms really quickly before we go deeper. FP32 just means 32-bit floating point numbers. It's a standard level of math precision, but it does take up a decent amount of memory.
Right, it's pretty heavy.
And CUDA is essentially NVIDIA's computing platform. It's the language that lets developers talk directly to the GPU.
Spot on. So the goal of this QR decomposition is to take a starting matrix, let's call it A, and break it apart into two separate matrices.
Right, a Q matrix, which is orthogonal, and an R matrix, which is upper triangular.
Exactly. And the contest didn't just ask for the final answer, it actually mandated a very specific method to get there, which is where those householder reflections come into play.
And this brings us to that brilliant analogy Sandkalp uses in his write-up. He says to think of a bathroom mirror.
I love this analogy.
It's so good because in a bathroom mirror, your reflection is exactly as far behind the glass as you are in front of it. So if you have a mathematical vector just sticking out in space, the mirror rule reflects it so that it lands perfectly flat on an axis.
Right. And in matrix terms, doing that zeroes out all the numbers below the diagonal of a column in one single shot.
Yeah, and to code this, you don't actually need to store the whole giant mirror. You just store the vector poking through the mirror, which is called v, and a scaling factor called tau.
What's fascinating here is why this specific, like mathematically elegant operation becomes an absolute nightmare for modern hardware to process.
Oh, because of the physical build of the GPUs.
Exactly. Modern GPUs are powered by these massive engines called tensor cores. And they're designed to do one thing incredibly well, which is chew through parallel matrix multiplications.
The GMs.
Right, the GMMs. They want massive, chunky blocks of parallel data.
So it's kind of like so if the math forces us into a strict sequence where step 2 relies entirely on step 1, aren't we just stuck? Like, how can an AI code its way out of a mathematical traffic jam? The fast lanes just can't handle it.
They can't. The serial work gets routed to the slow vector lanes, while the tensor cores just sit there idle, waiting for it to finish. But the fix is structural. It's what Sankalp and his AI swarm used, called the blocked householder algorithm.
Okay, how does that bypass the traffic jam?
Instead of doing the entire giant matrix sequentially, column by column, you pick a really narrow panel, say a block of just 32 or 64 columns.
Gotcha.
You accept that you have to do the slow serial work, but you can find it only to that tiny panel. Because it's narrow, the delay is minimal.
But wait, you still have the rest of the massive matrix just sitting there waiting to be updated. How do you handle all that bulk data?
This is where the magic happens. You take all those individual serial updates in the narrow panel, and you compress them into a single mathematical package.
Is that the rank B update thing?
Yes, the rank B update, often called the WI representation.
Which is that formula, identity minus V times T times V transpose.
Exactly. But the mechanism is what really matters. You take that entire compressed package of updates, and you just slam the trailing matrix with 3 massive back-to-back matrix multiplications.
Oh, I see. So instead of sending individual cars through a toll booth, one by one, the serial work, this WY representation packs all those cars onto a massive ferry.
That's a great way to put it.
Because the tensor cores are the ferry. They hate handling single cars, but they can easily move the entire block of cars across the water all at once.
Exactly. The serial work stays quarantined, and everything else turns into pure parallel matrix math. The tensor cores get to eat.
But, actually putting this into practice is the real seat here. Sankalp wasn't manually sitting there typing out all the CUDA and Triton code to make this blocked algorithm work.
No, not at all. He was doing what he called Codex maxing.
Right. And Triton, just for some context, is an open source programming language that makes writing efficient GPU code easier than writing raw CUDA. But he wasn't writing it.
Right. He was using the popcorn command line interface from the contest, which let his AI agents test code, run benchmarks, and submit straight to the leaderboard completely autonomously.
He wasn't using it like a glorified autocomplete. He built a whole ecosystem.
Yeah, we're really watching the shift from coding to agent orchestration here.
Yeah.
He set up this strict virtual laboratory.
With the problem statement file, right?
Yeah, problem statement markdown file for the math goal and an agent's markdown file for the rules of engagement, plus a super disciplined logging system, so every failure left a paper trail.
And the way he interacted with this lab is crazy. He used a command called /goal in Codex.
Right, the goal command.
Yeah, he'd give GPT 5.5 a very specific quantitative target, like beat our active best time on the 512 by 512 matrix shape, try different Triton configs, fix this loop, and keep iterating.
And the AI would just take off. It would loop autonomously for hours,
Yeah.
writing code, compiling it, reading hardware errors, and try again. Zero human intervention.
It's the ultimate tight feedback loop.
Totally. Normally, a human writes, tests, gets an error, stares at the screen, rewrites. Here, the AI had the compiler and profiler acting as immediate judges.
But Sankalp didn't just abandon it for the weekend. He used these /b2 or /side commands to check in.
Which is such a smart feature.
It really is. It's exactly like walking past a busy coworker's office and just slipping a note under the door. You don't break their flow. You just ask, hey, what algorithm are you testing? Are we winning?
You get a status update without stopping the background loop. And the early progress from this setup was just staggering.
Right, because the baseline path took about 419,000 microseconds.
And within a single day, just by getting Codex to write that blocked algorithm in Triton, the time for the 512 by 512 shape plummeted to 5,000 microseconds.
One day, to drop from 419,000 to 5,000. And if you are listening to this wondering how it applies to your work, the big takeaway is that we're moving past the point of micromanaging AI line by line.
Absolutely.
Like Sankalp noted, get out of the agent's way and only steer it back when it gets stuck.
But of course, as with any complex research, it did eventually get stuck.
Here's where it gets really interesting. Because around that 3,000 microsecond mark, that super fast progress just hit a massive brick wall.
Yeah, the AI fell into what data scientists call local maxima.
It was just endlessly tweaking tiny things, right? Like changing a memory block from 32 to 64 or flipping a gate, but no real structural leaps.
This really highlights a frontier problem with current AI. These models have immense compute, they know Triton syntax perfectly, they know the math, but they fundamentally lack research taste.
How would you define research taste here?
Well, when an AI is hill climbing, trying to optimize a score, it only takes a step if that step goes immediately up.
So if it runs a test and it's slower, it just kills it.
Immediately. It struggles to invent the next best experiment, especially if it requires taking 2 steps back to take 10 steps forward.
It doesn't have the intuition to say, hey, this is slower now because it's poorly aligned, but if we refine it, the ceiling is way higher.
Exactly. It's wearing blinders.
So how does Sandkelp fix that tunnel vision?
He enforced strict exploratory discipline. He put a beam search framework into his agent's markdown file.
Let's break that down. What does beam search look like when you're managing AI?
Instead of keeping one single best file, like a reigning champion code, and killing anything that didn't immediately beat it, he told the AI to camp 3 to 5 active idea families alive at the same time.
Like parallel tracks of research?
Exactly. These are the beams. He had an exploit beam for safe, incremental tweaks to the best code.
The safe bet.
Right. But he also forced it to maintain a near-miss beam.
A near-miss beam, how does that work?
Say the AI tries a radical memory allocation and it runs 5% slower. Normally, boom, delete it. The near-miss beam forces the AI to keep that code alive and tweak it. Maybe it was just one poorly tuned variable holding it back.
Oh, that makes so much sense.
And finally, a high-risk structural beam for completely wild mathematical approaches. He essentially programmed the AI to understand that ideas sometimes need time to mature before they win.
That's a classic human management tactic. You don't just fund the safe quarterly projects. You have an R&D department for the weird stuff too.
Exactly.
But even with beam search, Codex eventually ran out of ideas. And that is when Sandkelp did something even more strategic. He used a multi-model swarm.
The advisor model strategy. This is next-level orchestration.
He brought in Claude Pro, but not to write the final code. When Codex was out of ideas, Sandkelp instructed Codex to make headless API calls to Claude. He basically let his AI phone a friend.
It's just a beautiful division of labor.
Right. Codex sends the hardware profiling data and error logs to Claude. Claude analyzes it, brainstorms wild new hypotheses, and sends them back.
And then Codex, as the relentless executor, takes those creative ideas and actually writes and tests the CDA kernels.
One model is the creative brainstorming partner breaking the tunnel vision. The other is the engineer. And that diversity unlocked the final push.
It really did. Once the AI had permission to explore, it found some incredibly complex late-stage optimizations, like using a Cholesky RHR method, specifically for the massive 496 by 496 matrices.
Which sounds super technical. How does a Cholesky RHR method actually speed things up?
Cholesky is basically a mathematical shortcut for symmetric matrices. Instead of processing the whole dense grid, it breaks it down into simpler, lower triangular pieces.
So it just cuts the math in half.
Mechanically, yeah. The AI realized that at massive scales, paying the setup cost for Cholesky saves a huge amount of time on the back-end calculations.
It's a shortcut that only pays off on a long road trip. What else did the swarm figure out?
They implemented CDA graph replay.
Is that like caching a route on your GPS so the GPU doesn't recalculate the map every time?
That is precisely what it is. Every kernel launch has a tiny delay called launch overhead. For small matrices, that setup takes longer than the math.
Oh, wow.
Yeah. So CDA graph replay captures the execution path and stores it. The GPU runs the exact path repeatedly without paying the launch tax.
That's so efficient.
And they also figured out fused layout assemblies.
Meaning what for the data?
It means they stopped moving data around.
Yep.
Usually you calculate something, move it to memory, call it back for the next step. Fused layout assemblies mean assembling the data structures directly in the registers where they're needed.
Totally bypassing this slow trip to main memory.
Exactly, bypassing it entirely.
And all of that combined, the beam search, Claude as the advisor, Cholesky, CUDA graph replay, drove the time down from that stuck point of 3,000 microseconds all the way to the final 8,805.
Completing the 232x speedup.
So what does this all mean? We have an AI army doing 1,500 autonomous code submissions over 2 weeks. It sounds like the human engineer is becoming obsolete.
It does sound like that at first glance.
But the reality of Sandkelp's experiment points to the exact opposite. Even with massive automation, human domain expertise was still the ultimate secret weapon.
It absolutely was the limiting factor here. Sandkelp noted that his familiarity with machine learning lingo allowed him to prompt the models effectively.
He called it turning unknown unknowns into known unknowns.
Yes. For example, he knew to tell the AI to look into concepts like gated delta-net or shampoo-style optimizers.
Wait, for those of us not deep in the ML weeds, what are gated delta-net and shampoo?
Gated delta-net is a neural network architecture that handles sequential data efficiently. And shampoo is a really complex mathematical optimizer for training massive models.
But he didn't actually use those for this QR task, right?
No, the point is that his broad vocabulary let him ask the AI highly specific structural questions. If you don't know a concept exists, you can't tell the swarm to explore it.
And honestly, his lack of deeper specialized knowledge actually cost him the top spot, didn't it?
That is a really vital nuance. Sankalp admitted that his lack of deep, years-long expertise in GPU kernels kept him out of the top 10.
What did the engineers who beat him know that he didn't?
They knew to ask for hardware optimizations he didn't even know existed, like keeping the trailing matrix resident in FP16 memory.
FP16 meaning 16-bit precision, taking up half the memory footprint of FP32.
Yes. By casting data to a lower precision just for storage, they moved data through the memory buses twice as fast. They also wrote specialized data detectors.
Data detectors, how does that help?
If a matrix has a low rank, it means it's redundant and going to be full of zeros. The experts knew to write a quick check early on and command the GPU to just skip those massive blocks of math entirely.
And the AI swarm couldn't discover those tricks because it didn't know to look? And Sankalp didn't know to ask.
Exactly. The AI is a brilliant engine, but it still requires a human architect to lay down the tracks.
So if you're listening to this, whether you're writing GPU kernels, prepping a slide deck, or researching a novel, the application is identical. AI is not replacing the human director. It's demanding a much better one.
You can automate the execution, but you cannot automate the initial vision.
That captures it perfectly.
Which leaves us with a final thought to ponder. If we are truly entering an era where an AI swarm can autonomously test 1,500 complex hypotheses in 2 weeks, the most valuable skill isn't finding the answer anymore.
The AI will do that for you.
Right. The most valuable skill is having the research taste to know which question to ask next. It's the ability to look at infinite possibilities, recognize the subtle patterns of success, and guide the swarm. So how are you cultivating your own research taste in your daily work?
Because at the end of the day, you might have a tool that can speed up a process 232 times, but it is entirely up to you to point that immense power in the right direction.